we're going to take a look at an approximation algorithm for the metric k-center problem. And the technique that we're going to see is parametric pruning. So let's start with a metric k-center problem. It's a clustering problem modeled over a graph. So we have a complete graph with non-negative edge weights, which fulfill the triangle inequality. So it's a metric. What does that mean? For any pair of vertices, the cost of the corresponding edge should be smaller or equal to any cost that I can get by going via another edge. So if I go via this edge here, then if I take this cost plus that cost, that should be larger or equal to the cost of the edge itself. So then this is metric. For readability, I will not always show the complete graph. And now this problem is about selecting centers. So this will be the set S. So this will be a subset of the vertices. And if I have such a set of centers, then the cost for another vertex will be the cost of the cheapest edge to one of the centers. So I will call this the closest center for that point. So for instance, for this vertex here, assuming that the cost in my example correspond to the length of these edges, then the cheapest one will be this one to S1. And I can do this for all of the vertices. And so this one is between S1 and S2. It can simply pick one of those. We're really just interested in the cost itself and so on. So now you see with these orange edges always the cheapest cost to a center. And now the cost of this set S, so the set of centers, is the maximum cost of any vertex. So in my example, this would be this cost here. And now what we want to do is, of course, we want to minimize this cost over all possible choices of the centers. Of course, we need a somewhat more constrained problem, because otherwise we could simply make every vertex a center point. So that's where the k comes in place. So the problem also has a parameter k as input, and we're looking for the set S of k elements, which minimizes the maximum distance to one of the centers. So in this example, k is 3, let's say. Is this already an optimal solution? Meaning, can we select 3 center points such that the cost is smaller than this? Yeah, so here obviously a choice like this, if you take that, so now in orange you see again for every vertex the cheapest one, and this would be the maximum here. So this might be actually a minimum cost k center solution. What we're going to see today is a 2 approximation. So the problems that we had, we're going to see a 2 approximation. And the technique that we're going to use is parametric pruning, which I first want to introduce somewhat abstractly, and then we're going to see what this means for the metric k-center problem. So what are the ingredients of parametric pruning? So first of all, we have an optimization problem. We want to, given k and this graph, minimize the cost of the clustering. And we're going to reduce this optimization problem to a decision problem. Yeah, so this is typically possible. The corresponding decision problem is then the problem asking, is there for a given parameter t, so that's where the parameterization comes from, for a given parameter t, is there a feasible solution? So is there a set S in our case with cost at most t? So this is a decision problem corresponding to the optimization problem. And if we could answer this decision problem, then by running it for increasing values of t, then we could answer the optimization problem. So simply we run it up to the t where the answer switches from no to yes, and then this yes would be a solution to the optimization problem. The corresponding value of t would then be the cost. Now, this is ingredient number 1 for parametric pruning. Then obviously pruning itself. So what is a pruning here? We start with an instance for the optimization problem. And now we have a decision problem corresponding to this parameter t here. And the idea is, because we now have to some extent a simpler problem, this decision problem to solve, we can also simplify our instance. So we're not working on the original instance, but we're going to simplify it. Specifically for this value of t, we'll get an instance which we now want to solve our problem on. And the idea is that we can remove anything that is not relevant for solving the decision problem. So in our example, in the k-center setting, imagine we have this complete graph and we have a t which tells us what is the maximum cost that we want to allow. Then obviously all edges with a larger cost we can take out of the graph because we know those we cannot use anyway. And then we have a smaller graph to work with. Also, we can then on the smaller graph ignore all of the edge weights because we know that all of the remaining edges have cost smaller equal t. But we're going to see this in more detail in a moment. First, let's put in our last ingredients, and that is, of course, for approximation algorithms, we will have to somehow find lower bounds. And for parametric pruning, we do it in the following way. We essentially have 2 steps, although as you will see, the steps are essentially done in one. So step 1 is we're going to use a family of instances. So we're going to increase t and we're going to use this to compute a lower bound for opt. So a t star, for which we know t star is smaller equal opt, or opt larger equal t star. Imagine we have these instances. So for small t, the answer will be no, there's no solution. Then at some point, okay, we would want to switch to yes, but we have a point where we don't switch to yes, but where we essentially a lower bound at that point fails. And at the point where our lower bound, so the largest lower bound that we get, there we want to take this t star here and then find a solution. Find a solution in the instance alpha times t star, and alpha is then our approximation factor. So in our case, alpha will be 2. So we'll have to find a solution in the instance with 2 times t star. Now let's apply this in the setting of metric k-center. So we have to think about what is our decision problem and how do the pruned instances look like. So the decision problem is a question, give me a value t. Is there a selection of centers, or k-centers, or size S of size k, such that its cost is smaller equal t. But we will not need to test all values of t. We only need to take those values which opt might actually attain. And those are actually only the edge costs that occur. So the optimal solution, whatever its cost will be, has to be a cost of an edge that actually exists. So I will only consider those values as t. And if I want to do those in increasing order, what I do, I take my set of all edges, I sort them by their cost from small to large, and then my t I'm going to increase along going through all of these costs. Now let's assume I'm currently testing the cost of the edge ej. Now let's think about how my pruned instance looks like. So a simple way to describe the pruned instance here is the following. I'm going to take the graph gj, which only includes the edges e1 to ej. This will include all edges that are of cost smaller than ej. And if there are more edges which have exactly the same cost as ej, what we're actually going to do here, so for those, they will in this order occur in an arbitrary order if they have the same cost. And I'm at this point only including those that come earlier in the order. But that is not really a problem, just a technicality to be aware of. But then I now can simply go through all of those gj, starting with g1, g2, and so on. Now, what have we gained? So something that we have gained is now that we do not have this complete graph anymore, and we do not have edge costs anymore, because for this pruned graph Gj, if I want to test is there a set of centers, then the only information that I need to have is the following. For any of these vertices, if this would be my selection of centers, is there a vertex in this set of centers for which I have an edge to that center, because these edges have all lengths smaller equal Cej, so they are all edges which for my decision problem are okay. So what I described here actually corresponds to a graph concept, namely the concept of dominating sets. So a subset of the vertices, let's call it D, is dominating in a graph H if for each vertex, that vertex is either in D itself or it is adjacent to a vertex in D. So in my example, the set of 3 green vertices is dominating because for any other vertex, this one, it is, okay, either it's one of those 3 vertices or at least it has an edge to at least one of those vertices. Yeah, so this is a dominating set. We will denote here by dom of H the size of the smallest dominating set. So the cardinality of the smallest dominating set. And the problem that we now actually want to solve, so our decision problem for the K-center problem, is a question of whether in Gj there is a dominating set of size at most k, so whether this number here is smaller equal k. Yeah, so this is now our reformulation of our decision problem in the pruned instance. Now this does not help us directly because the problem of computing the size of the smallest dominating set is actually NP hard. But we're now going to use this in an approximation algorithm. The key ingredient is this concept of a square of a graph. Let me first illustrate the idea of where we're heading to. So in terms of a lower bound, what we want to find is a maximal set of vertices such that these vertices will have to connect to different centers. Let me illustrate this by just pointing at 2 vertices here. If you look at those 2 vertices here, obviously they cannot be in the same cluster. So they cannot have the cheapest edge, or here just the edge, or the dominating vertex, the vertex from the dominating set that they would connect to cannot be the same because they do not share a common neighbor and also are not neighboring themselves. Yeah, so here I could already conclude that I will need at least 2 vertices in my dominating set because one vertex could not cover those 2. This we will formalize. So the idea is if we have a maximal set of vertices that have to connect to different centers, we will show that this actually then also gives us an approximate solution. But let's start with the first part. And the concept here that we're using is a square of a graph. So the square of a graph is again a graph with the following property. So we have the same set of vertices, but we will have an edge between 2 vertices, between 2 different vertices, if they are either adjacent in H or they have graph distance 2. I can connect them by going via 2 edges. So let's do this by example. This vertex, if I now want to know which other vertices are adjacent to this vertex in Gj squared, so in the square of Gj, then first of all, obviously all of those that have graph distance 1, so which are adjacent to this vertex, but then also those that are adjacent to these vertices. That then also includes the vertex up here, and then from here I can also reach this one and that one. So all of these vertices will be adjacent to U in this square of Gj. Let's do a second example. If I look at U prime, so who is neighboring U prime? So of course the 2 vertices that are adjacent to U prime, but then also those that are adjacent to those vertices. If you look at those two and you look at gj squared, now we actually have a dominating set in gj squared. So every vertex other than u and u prime is adjacent either to u or u prime. And why is that interesting? So here's an observation that will help us to design our approximation algorithm. Let's assume we already know that the optimum is at least Cej. Then if I have a dominating set of at most k vertices in gj squared, or here for instance, let's say k is 2, then I have such a set, then this is a true approximation for the metric case center. So why isn't that the case? So let's say we have such a dominating set, in my case u and u prime. Then what I have is every other vertex is adjacent to these vertices in gj squared, meaning that in gj any other vertex has graph distance at most 2 to at least one of those centers. So let's take for instance this vertex here, so it has in particular also graph distance 2 to u. So what can I conclude from that? It means that if I use, there are two edges, that I have this path of length 2 that connects those two vertices. Now if you think about all of these edges in the graph, I know that for each of these edges their cost is smaller equal Cej. So this is true for both of those edges. Now the question is what is the cost of the edge between those two vertices we're now talking about the original graph G. Now because of triangle inequality, the edge between those two has to be at most the cost here and the cost there, which is 2 times, bounded by 2 times Cej. So this follows from triangle inequality that in the original graph this edge has to have a cost smaller equal this plus that cost. And now we put in this assumption, so we were assuming opt is larger equal Cej, so I can write here smaller equal 2 times opt, and this is already what I needed for this observation. So now we know that if we have a lower bound and we have a dominating set, things work out. Now we just have to make sure that we get both of these at the same time, the lower bound and a dominating set of size k. For this we need another ingredient, and those are independent sets. So those we already saw when we designed the greedy approximation algorithm for set cover. So what is an independent set? I have a graph and a vertex set, so a subset of the vertices is called independent if between any pair there's no edge. So let's start here. So this is obviously an independent set because I only have a vertex. This is still independent, these two, because there's no edge between those two vertices. And I can increase my set further and further until at some point any vertex that I would add would violate this property. And this is now a maximal independent set because I cannot add one more vertex and still have an independent set. It is not necessarily the maximum independent set, so there might be a larger one, but the observation here is in this case simply that I cannot to the given set add any vertex. And why are maximal independent sets interesting? Because they are also dominating. So any maximal independent set is a dominating set, which is easy to see because assuming I have a maximal independent set which is not dominating, that means there is a vertex which is not adjacent to any of the vertices that I have so far, but then I can simply add it to my independent set and get a larger independent set. So here now I already have a connection between maximal independent sets and dominating sets, but I will need to have a lower bound on the size of the smallest dominating set, and for this I can use the following lemma, and that is, let's assume I have an independent set in the square of a graph, then the size of this independent set is a lower bound on the smallest size of the smallest dominating set in the graph itself. So this will allow us to get a lower bound on opt. To prove this lemma, we should look at how a dominating set H looks like in H squared. So let's have a dominating set in H. So those two green vertices, if this is H, are a dominating set. A way to look at dominating sets is the following. If for every vertex here, I now consider the star for that vertex, meaning I'll take all of the edges adjacent to that vertex. Now, if I do this for all of the vertices in the dominating set, so I look at all of those stars, so this will now include all vertices. Yeah, and the dominating set in the center of the stars. Now, what if I look at one such star, so then let's look at this star here, and look at how the graph looks like on those vertices in H squared, then we have the following. Because it's a star, for any two vertices in the star, the distance, the graph distance in H, is at most 2. So any two vertices in a star are at most 2 edges apart. But this now means that in the square, where I have an edge whenever the distance is at most 2, the star will be a clique. So I will have on these vertices of a star a complete graph. And this is true for this star, this is also true for that star. So a star in H will give me a clique in H squared. So why is this now interesting? So if I now look at independent sets in H squared, then in any of these cliques, such an independent set can have at most one vertex. So here I consider a clique. And obviously, as soon as I have picked one vertex in that clique for my independent set, because it's a complete graph, so this vertex is adjacent to all other vertices in the clique, no of the other vertices can be selected. So for each of these cliques, I can have at most one vertex in my independent set I. But this means that for each of the stars, I can have at most one vertex in my set I. And that means, so I have at most one vertex in the independent set per star. The number of stars corresponds to the size of the dominating set, meaning that the size of the independent set will have to be smaller or equal to the size of the dominating set, and in particular smaller or equal to the size of the smallest dominating set. So this proves the lemma. Now we have all ingredients in place for our algorithm. So let's describe an algorithm, and we are going to take all of the edges, we sort them by cost, and then run through those from smallest cost to largest. We are going to look at the graph Gj, or more specifically its square. So we only need to construct the square of the graph Gj. And in that graph, we're now going to find a maximal independent set. So this we can simply greedily select vertices until we have a maximal independent set. Now we're going to look at the size of that set. And if that size is smaller or equal to k, we're going to return the independent set, our maximal independent set, as a solution. Let's prove that this is indeed a true approximation, and we do this in 2 steps. So first we will establish our lower bound, and that we do with the following lemma. So this lemma tells us that at the point where the algorithm stops, so the j that where it stops, we have that the cost of ej is smaller or equal opt. And why is that the case? So we stop as soon as we found a maximal independent set of size smaller or equal k. What does that mean? That for all previous iterations, so for all smaller I, we actually found a maximum independent set of size larger than k. And with the lemma from the previous slide, what we have is that the smallest dominating set has at least the size of any independent set. And if that independent set had size larger than k, which it had for all previous iterations, otherwise we would have stopped earlier, we know that the dominating set has also size larger than k, and that means that for all previous iterations, the t's, so the CEIs that we considered, there we did not yet have a feasible solution. So opt has to be larger, and we can put this together with the observations that we already had, namely that for one, this independent set here, so a maximal independent set is always a dominating set. So ij is a dominating set, and then we said if we have a dominating set in the square and we have that Cej is a lower bound for opt, then this dominating set is already a true approximation, and that's exactly what we make use of here. So let's also use this algorithm to recap the technique that we were using. Parametric pruning. So what does parametric pruning do? We reduce the optimization problem to a decision problem. Here's a decision problem with asking whether there is a solution with cost smaller equal Cej. And then we work on the pruned instance. So the pruned instance here was Gj, and actually we then worked on a derivation of that Gj squared. It's a square. And we use that to derive a lower bound. This is what happened in this lemma. And then this lower bound in combination with a solution which is at most a factor alpha larger than this lower bound, which is this solution here, we get our alpha approximation. So here's an example that shows that the approximation factor is tight. We have these blue edges, they have cost 1, the brown edges have cost 2. Now the algorithm will first sort the costs of the edges, meaning it will process the blue edges in some order and it would then process the brown edges later. So before we have all of the 4 blue edges, let's say k is 1 here. K is 1. We want to have 1 cluster, so as long as one of the blue edges is missing, we will need 2 clusters anyway. Or we'll also find a maximum independent set of size 2 because we have 2 disconnected components. So at the point where we have all of those blue edges, then the square of the graph is simply the whole graph here, or at least those edges. And at that point, whatever vertex we pick is already a maximal independent set. So let's say we pick this vertex, that's a maximal independent set, but its cost is 2 because this one has distance 2 to it, while we could have simply picked the middle one and that would have had cost 1. So this algorithm is indeed just a true approximation, but here we can actually prove that we cannot do better. So unless p equals np, there's no polynomial time algorithm with an approximation factor of 2 minus epsilon for any epsilon larger 0. And we can prove this. So this is like an NP hardness reduction, just that we also keep track of the approximation factor. We reduce from dominating set to the metric k-center problem. So for the dominating set problem, the input is a graph, so now not a complete graph, but an arbitrary graph, and an integer k, and we ask, does this graph have a dominating set of size k? So for instance, for k is 1, the answer would be no. For k is 2, the answer would be yes, because these two, if I pick those two, then any vertex is either one of those two or is adjacent to them. Now we are going to transform this to an instance of the metric k-center problem in the following way. So we want to have a complete graph. So G prime will be a complete graph where I take these edges. So I take the original vertices, I take these edges, I take additional edges to make the graph complete. And the edge cost will be 1 for the original edges and 2 for the remaining edges. Now the cost of a solution to the K-center problem is now closely linked to the question of whether there is a dominating set in the original graph. More specifically, let's say I have a solution to the metric K-center problem in this graph G prime. If there is a dominating set in the original graph, then this solution, so the one with minimal cost, will actually have cost 1, because I can simply take the dominating set in G and take that as my solution, and because every of the other vertices is adjacent to these vertices, every vertex has an edge of cost 1 to one of the centers, and therefore the clustering has cost 1. So for instance, if K is 2, there is a solution, a dominating set of size 2 in G, and I can use this also as my set of centers. On the other hand, if there's no dominating set of size K, so any dominating set has size larger K, then also the cost of the clustering is at least 2. So for instance, if we take K as 1, then there is no dominating set in this graph. Of course, for the K-center problem, there's still a solution. So this would be a solution. But because the solution cannot be a dominating set in G, there will be at least one vertex which is not adjacent to any of the points in the center in the original graph, and that one will have edges of cost 2 to all of the centers, and that will give me a solution of. So now you might wonder, why do we have to have the 2 here? So the 2 is here because of the metric property, so because of the triangle inequality. I cannot make a larger increase this cost further, because now, for instance, if I would want to give this edge here a larger cost, then because there's one of cost 1 and edge of cost 1 here and there, because of triangle inequality, the maximum that I could have here is 2, and that's what I also picked. Now I claim that this observation here already proves our theorem. Let me illustrate this by, for instance, assuming that there is a 1.5 approximation for the K-center problem, and why that would lead to a contradiction. So if you would have a 1.5 approximation, polynomial time 1.5 approximation, then what I could do to solve the dominating set problem, I transform it in exactly this way to the K-center problem. I can solve it. And now I know that one of two things could happen. So if there is a dominating set, then the cost of the optimum will be 1, meaning my algorithm will return a value between 1 and 1.5. So definitely a value smaller than 2. So the algorithm will return a value smaller than 2 in this case. But if there's no dominating set, then the optimum will have a cost of 2, and then my algorithm will return also a value of at least 2. Meaning, depending on whether my algorithm returns a value of smaller 2 or larger equal to 2, I directly know whether there is a dominating set in the original graph, yes or no. That means I would be able to solve NP-hard problem in polynomial time with my approximation algorithm, and that would only be possible if P actually equals NP. Now let's generalize this problem, or look at a variant, namely the metric weighted center problem. So we've seen the metric K-center problem, but instead of having this K, we will now look at a weighted version of this. So instead of saying I want to have at most K centers, every vertex will now have a non-negative weight, and we are going to have a budget. So this will be part of the input. And now the question is, I want to select a set of vertices so that I stay within the budget. So the sum of the weights should stay smaller equal our budget. And among all such choices, I want to minimize the cost of the clustering. So let me show you a small example. So here's the vertex weights are illustrated by the size. So we have weights 1, 2, and 3. Now I have these 2 green vertices, and the question is this an optimal solution for a budget of 4? And of course not, because this is not even a feasible solution. So these two green ones together would have a weight of 6, so I cannot select them. Optimal solution could, for instance, be this one here. So I have 3 vertices of weight 1. So with that, I stay in my budget, which I said was 4. Of course, I could also select 2 of weight 2, or 2 of weight 1 and 1 of weight 2. So this is a metric weighted center problem, and what we want to see now is a 3 approximation, and it is just a very slight variation of the algorithm that we've already seen. So this is essentially the framework of the algorithm that we've seen, which we are now going to adapt to get a weighted version. And interestingly, we're going to do here the same as before. We will find a maximal independent set in the square. So at this point, we have not used the weights yet, which we obviously have to use. But what we're now going to do is the following. So for each of the vertices in this maximal independent set, so let's say this is such a vertex, this is its neighborhood in Gj. Now, of those neighbors, and including U itself, I am now taking the lightest vertex, so lightest node, meaning the one with the smallest weight. Let's call this Sj of U. This is the lightest node in the neighborhood. And now, instead of taking Ij as a set of centers, I'm now going to take the set of Sj. So for each of the U's in the independent set, I'm going to take the lightest node in the neighborhood, and I'm going to include that in my potential set of centers. Now we again need 2 ingredients, the lower bound, and if we have the lower bound, then we find a solution within factor 3. So to first argue the factor 3, so what we had seen in the previous algorithm, if we would have taken U here, then in terms of the cost of the solution, we get a factor of 2 because any vertex is in distance at most, in graph distance at most 2 to such a vertex of the independent set, and therefore using triangle inequality, the cost of the edge in the original graph from any such vertex to one of the U's is at most 2Cej. Now, we cannot simply take U because the weight might be too large, but for Sj, we have that it has graph distance 1 to U. Therefore, every vertex has a graph distance of 3 to such an Sj because it has graph distance 2 to an U, and then one step further to the lightest vertex in the neighborhood of that U. So here we have a graph distance of 3 in Gj, which corresponds to a cost of at most 3 times Cej in the original graph. So this we get this 3 times Cej we get because of triangle inequality. So now we just need a lower bound, and this is very similar to what we had previously. So now instead of having to set the size of an independent set in relation to the size of any dominating set, we have to set the weight of Sj into relation of the weight, minimum weight of a dominating set. So let's say H is a weighted graph, so vertex is a weighted graph. I is an independent set in the square. S is a set of lightest neighbors of the vertices in I. So this is exactly my Sj here. Then the weight of S is smaller or equal to the smallest weight of a dominating set of H. And this follows in a similar way as before. So before we were arguing coming from the stars to the cliques that if I have a dominating set, any vertex in the dominating set has at most one of the vertices of an independent set in its neighborhood. So meaning if I have now one such independent vertex of an independent set in the neighborhood, I look at its lightest neighbor. The weight of that lightest vertex in that neighborhood is smaller or equal the weight of the corresponding vertex in the dominating set. Yeah, because it's the lightest one in the neighborhood and the dominating one is also in the neighborhood. So I can lower bound for that vertex of in the dominating set the weight by that lightest node. And since I can do that for all of the vertices in the dominating set, I get this bound, and I can overall conclude that I here have a 3 approximation. Now let's again look at a tight example. So here you now need to define a graph, a metric one, and a suitable budget. Our budget will be 3. The graph will be as follows. So we have this vertex A with weight 1, B, C, and D all have weight 2. And I have edges of cost 1 between A and B, between B and C and D. And additionally, I have a bunch of vertices which all connect to A with a cost of 1 plus epsilon, and they all have weight 4. So from this we already can conclude, because our budget is 3, none of these vertices are allowed to be included in our solution. And now we of course should have a complete graph. So what about the other edges? We are going to use metric completion. That means for any other edge we take as the cost simply the cost of the shortest path in the given graph here. So for instance, if I take this vertex and C, then the shortest path uses 1 plus epsilon here, 1 here, 1 here. So that's 3 plus epsilon. So this edge here in the complete graph will simply get weight 3 plus epsilon. Now, what is the optimum and what does the algorithm return? Now, our budget is 3. The optimum would be the following. We pick A and C, and then the cost is 1 plus epsilon. What would the algorithm do? So the algorithm again sorts the edges by weight, and so it would first add the edges of weight 1, but at this point these red vertices are still all disconnected, and therefore, because I cannot pick those because the cost is too high, certainly I cannot find a suitable set. Only at the point where all of those are connected to A. But at that point now in the square we have that all vertices are in the neighborhood. At this point, with 2 steps, I can reach any vertex from B. So B is a maximal independent set. Now what did the algorithm do? It did not simply pick B, but it took the vertex, the lightest vertex in the neighborhood of B, and that is A. So the solution which the algorithm then would give is simply it would give out back A. A is a feasible solution because that way has weight 1 and we have a budget of 3, but the cost that we get now is 3. And that means we indeed only have a 3 approximation here. Or it's 3 divided by 1 plus epsilon, and we can make epsilon arbitrarily small. We could also not include the epsilon. The reason we do it here because it makes our life easier in terms of the order of the edges, because 1 plus epsilon here guarantees that those edges here are added last. Of course, I could, since algorithms sort these arbitrarily, also simply set all of these costs to 1 and say we simply assume that the algorithm adds these last. So what have we seen? As a technique, we have seen parametric pruning, so reducing to the decision problem, using a pruned instance for the decision problem, and there looking at that family, finding a lower bound, and then when we found the lower bound, also find a solution which is at most a factor alpha away of that. Then we saw the 2 approximation for the metric k-center problem and the 3 approximation for the metric weighted center problem. Finally, let me mention another 2 approximation, actually a very simple greedy algorithm. Works as follows. You take an arbitrary vertex as the first vertex to include an S. Then you look at the cost for the other vertices. So the cost now being the cost of the edge to that first center. You take the one with the largest cost. And then of the remaining ones, you take again look at the cost of that vertex, so the cheapest cost to one of the 2, And then you take again the one with the maximum, so the one that is kind of furthest away to its closest center. And then you do that again and again and again until you have k vertices. And this also gives us a true approximation for the metric k-center problem.